Hello physics students, welcome to video number 3 in gravity, and let's get into the serious business of equations that relate to the law of universal gravitation. Now the law of universal gravitation describes gravity in the entire universe, and it also describes it on all scales, from an electron orbiting around a nucleus to the way spiral galaxies work. So, first of all, what is gravity? Now, our definition of gravity is basically the force of attraction between masses. So, any two masses, no matter how large or how small, they have a gravity field around them, and the interaction of those gravity fields gives us what we call gravity. And so, to quantify it, let's imagine we have two masses, m1 and m2. We have a distance from their center of masses d, and the force of gravity is given by this equation here. And it doesn't matter the relative size of the masses, it doesn't matter how big or how small they are, how close or how far they are, this equation describes it, and that's why it's a law of universal gravitation. Now, some equations will use d as the distance between, or some textbooks will use d as the distance between the center of two masses, and some will use r. Now, you'll also notice there's a G. Now this is straight off our information sheet, and so this is what it looks like for you guys. And G here is a constant, and it's a constant that has been determined, and its value is 6.6 times 10 to the minus 11, and it has a whole string of units here. Now this is again off your information sheet. And the purpose of these units is sometimes confuses students, like how can you have Newton meters squared kilograms per to the minus 2. Now basically these units here reflect the fact that we would use standard units in this equation. So our masses would be in kilograms, our distance would be in meters, and that would give us a force then in newtons. So this constant is dependent on the units that we use. If we went back in time, back to when we were using the imperial system, these values would be different because we wouldn't be using kilograms and meters, and so the constant would have a different value. It is still a constant, and it's a constant so that if you put kilograms and meters in here, you get newtons. Alright? And that's just on our equation. So generally speaking, most common questions just give you two masses and a distance, and you have to work out the force, or vice versa. You'll be always given enough information to use that equation and rearrange it. The thing I say to students most commonly is don't forget the square. There's a square here, and students just keep forgetting it. And there's a couple of other squares in some of the equations we use, and the number of times students forget to do the square is amazing. Right, now the gravitational constant. Now how was that worked out? Well, it was first determined in 1798 by Henry Cavendish, which is a fair while ago. And the system he used, that's what he looks like, no photographs back then. The system he used was he had a torsion balance. And so basically he had two very large masses, probably steel or something, and they were set up to rotate around an axis, and to rotate fairly freely around an axis, and he could rearrange them. And then he had two smaller masses, these two masses, and so basically he was duplicating F equals G m1 m2 on r squared, so doing it there but also doing it there, so he's getting effectively twice the accuracy, but it also meant that the setup was easier to balance. And so he could duplicate both sides, and so he would move these large spheres distances away from the smaller spheres, and he would have a very fine, basically a hairline microscale that he would look through a window and measure how much force it took to exert on each of those, and whether it was basically it's a force of attraction, so he could measure that. And he, through a numerous observations, very careful observations, he was able to come up with a value very close to the modern value. So he was a very careful scientist. Now this was all inside a room, so that there was no air drafts that could move the spheres. Now you can buy a modern day version of it, and if you go off to uni you might well be using some of this apparatus just to verify that it is true. And so because it's more sensitive nowadays with our electronics, the spheres don't have to be as big, but basically the setup is effectively the same. So here we have large heavy spheres of steel or lead or something, and some smaller spheres as well. And then there's a very fine hairline torsion which you twist, and you can measure how much force it takes to move the spheres from their position. Now you can go on the internet and buy your own. Why not? Now the equations you're going to use, let's make these pop up, are these guys. This is the force of gravity equals mass times the acceleration due to gravity, and that's a variation of F equals ma. This is the one we would most commonly use in gravity, and we're going to talk about these guys in some later videos. This G is what's called the gravitational field strength, and that's a measure of how strong the gravity is in a particular area. And this is a rearrangement that we use for satellites. And in terms of constants, we would use 9.81 as our acceleration due to gravity on the surface of the Earth, and that's our gravitational constant. So let's do a quick example. Determine the force of attraction between the Earth, and you're given the mass in kilograms, and the Moon, and we're given the mass of the Moon, given that the Earth-Moon distance is. Now if we're not told otherwise, we'll assume that this mass is centre of mass to centre of mass. Sometimes they trick you up by talking about the surface distance, and then you have to add the radius of the planet or body, and you just got to look out for those, but you'll get some examples of those in our workbook. Now what do? We would just notice that we've got a few things here. We would, when we're starting out, we just circle the information that we have and that we're given, and recognize it's a gravity question, so we're looking for these things that we can put into the equation. We've got one mass, we've got a distance, and we've got a second mass. Okay, and we've got G as a constant, so we should be able to work that out straight away. And let's get rid of that writing, we don't need that there. Right, and putting the numbers in. And what I would say here is, now this example, they've done everything on the one equation, and I would recommend that you at least set that out, but I would also recommend that you put brackets here. I'm using my mouse to draw with because my graphic tablet's not working, and just as they put brackets here, I would put brackets in here, and make sure that you're using your EXP button on your calculator, so that effectively your calculator is putting brackets in there. The other thing that students have a tendency to do is they try and do this whole equation in one go, and that's where they either forget the square or they punch it into the calculator, and because the calculator does calculations from left to right, much like a computer if you're programming a computer, it doesn't necessarily do what they think it's doing, and so they won't come up with this answer. What I recommend is that between this section of working and the answer, you have a couple of other lines of working. One line of working would be to work out the value that these three numbers represent, and you type that in and then you write that down. The other step would be to work out what the square of this value is, and you write that down, and then you do the division of those two numbers, and you should get this number. Alright, now as you're doing these questions, if you keep getting the wrong answer or you keep getting the wrong powers that we're raising things to, come and see me, because you're probably doing something wrong with your calculator. You're probably attempting it correctly, but you're just programming your calculator the wrong way, and that's a common mistake. Right, let's get rid of that writing again. And so what we can conclude from this is There is a force of attraction between masses, whether they're large or small. In this example, very large masses, and they're separated by a large distance, but the force is still there. This force is actually the force that causes the moon to go round the Earth, and we would call that a centripetal force because it's a circular motion. So the centripetal force that causes the moon to go around the Earth is provided by gravity. And that's what also allows a lot of examples that we're going to look at that we would call satellite motion. That it's actually gravity providing the centripetal force that allows satellites to do what satellites do. So in the next video we're actually going to look at satellites. Okay, cheerio!